Perfect. Awesome. So yeah, today is Friday, February 13th, 9 a.m. We're talking with Steve Lehar and Richard Watson, and I'm Charlie Munford. And we're talking about harmonic resonance, the pistolution, the definition of agency, and we've just founded the Agential Biology Institute, and we've asked Steve to be part of the scientific advisory board. And so we are off we go. Yeah, great. Um, yeah, Steve, the main thing, I mean, we talked, we corresponded over email about this, but um, the main thing is that, I wanted to have right now a scientific conversation about where Richard and I are about, thinking about resonance and how it might or might not play into this um, question of agency. And we're having this discussion about the definition of agency and how to test for it across different domains. So we've, as you saw in the research proposal, we've set this sort of this collaboration up that goes across several domains, computational modeling, um, smart machines, you know, chemical agency, autocatalytic sets, that sort of thing. And then organismic agency, which is like bioelectricity and um, cell behavior of anthrobots, sort of non cells that don't have an evolutionary history. And then we've got an evolutionary experiment. So there's five different domains where we're trying to come up with uniform tests for agency. And right now, our hypothesis, not necessarily the hypothesis of everyone in the project, but Richard and I's hypothesis is that this is somehow based on harmonic resonance. And so I was hoping we could talk to you about, what we've been thinking about and how it lands for you, and you could give us advice.
Well, I think a lot of this is kind of at the philosophical level. For example, what do you say to my proposal that positive and negative charges love each other with a passion that is so strong that you can't keep them apart? They snap together and hold together for dear love, and that unless we recognize the similarity between, the agency of single particles, single charges, the fact that they are charged fills them with desire. And if we don't recognize that, then we'll never get anywhere. That's my, general thought. And once you understand that, and you look at how electrons stack up in an atom as you increase their proton number, and how they jostle for position in a harmonic way in the electronic orbit, that's, if you believe that, then you don't need any further convincing. If you don't believe, you're completely hopeless. There's no talking.
Yeah, I'm with you, Steve. So I think you're right that there isn't any difference in kind between the attraction of fundamental particles and the attraction uh, that we call love at the human level. There is a difference in specificity, though. So any old positively charged particle feels an attraction for pretty much any old negatively charged particle. But the specificity of the attraction between high level agents, what they are drawn towards, what they are attracted to, not just in a interpersonal sense, but in, what environments are attractive, what behaviors are attractive, what interactions with other animate things in their environment are engaging, tends to be much more specific because it's much more high dimensional. Does that make sense to you?
Yeah, although I think there's like a gradation in between.
Yeah.
when looking at single pairs of plus minus particles, then yes, you're right. But if you look at electrons stacking up in layers and kind of jostling with each other for position and influenced by other forces nearby that can induce an electron to pop out or to pop back in again, that there,
Yeah.
that the harmonic resonance, cooperation, competition, interaction between electrons in electron shells is really a very complicated and subtle and patterned process, and it's harmonic resonance right there at the very bottom. But
Yeah. I think that's right.
when you stack molecules together and you start to get, molecule to molecule interactions, and you get a chunk of matter, a little tiny chunk of matter, and you look at its behavior under different electrostatic conditions, that is a continuum all the way up.
Yeah.
And the very bottom is so compellingly similar to the very top that, to me, that's that's the way it happens.
Yeah.
I
So
might.
if we take just a couple of levels up from subatomic particles, we're already at the table of elements and the nature of covalent bonds and the specificity of those is quite a complex systematic language of possibilities. And yeah, the only difference between one and another, well, they're made of the same stuff, right? They're made of the same fundamental subatomic particles. It's the partly it's the numbers, it's the quantities, but mostly it's the shape of the dance that they're in that matters to the kind of interaction that they have with other dances of other shapes.
Yeah, yeah,
Yeah. I think that's right. So the there will be interesting questions to do with what are the fundamental properties that make apparently simple systems capable of building complex languages like that? And what are the conditions under which systems develop significant depth to their agency, to their specificity, to the language of their communication, to their ability to perceive, memorize, learn about one another, right?
yeah.
So individual subatomic particles, we imagine, are not very specific, can't learn very much, don't have much memory, etc. Uh, Chemical elements, we might put a notch or two higher. And living organisms, individual single-celled organisms, um, we can begin to do quantifiable observations about the kind of memory they have, the kind of learning they have, the kind of adaptive behavior that they have, in a sense which is beginning to look meaningful to what we mean by those things, right? The kind of behaviors where people would say, yes, okay, magnets can't do that, right? But
Yeah.
but single-celled organisms can. So the research questions are, there's mm, a philosophical preference about what language you want to use for subatomic particles and whether you think it's valuable to use language like agency at that level or attraction in the same sense that we use it for higher level organisms. But regardless of that philosophical preference, there are concrete there's a concrete research agenda about understanding the conditions which deepen those levels and make them more specific and make them more cognitively capable, right? So that's the
Yeah.
stuff that we want to focus on.
Well, how about focus on one very important intermediate level, and that is the a biological membrane. The bilayer, what is it called? When you get the hydrophilic ends and the hydrophobic ends, and they start to, these individual elements start to self-assemble into sheets. And the
Hmm.
sheets have a certain intelligence that you observe in the amoeba that part of their logic is their physical arrangement in the membrane, a little bit like if you've studied like medieval battles or Roman ancient battles where soldiers line up. All right. And it's no longer the individual soldier that matters, it's the membrane that they make. And if you can break the membrane, plow through in one spot, you burst that membrane and you win the battle. So the logic of military battles is the same as the logic of biological membranes.
Mm. Not entirely unlike Go.
Yes.
Um, yes, I think that's right. If you took the chemical milieu from inside an amoeba and you put it in a test tube, it's not as smart as the amoeba anymore, right? The
Right.
intelligence isn't inside the amoeba. And
No.
likewise, if you took the bilipid layer and you, I don't know what, stretched it out flat, that doesn't have any intelligence either. But the interaction between the internal dynamics and their ability to structure and be modulated by the shape of the membrane is something that neither one can do on their own, right?
Yeah. Yeah, it's like you can't even understand what's happening unless you move to the higher level and see like a line of soldiers, not as a bunch of individuals, but of a membrane. And the
Yeah.
individuals join and leave the membrane during the battle. But the membrane itself must maintain its integrity, and the laws of interaction of these membranes it is an explanation at a higher level than the individual. It's almost like you have to start all over
Yes.
again with,
Subject to topological logic, if that's not a
you know,
redundancy, rather than particulate logic. Yeah.
right, and also kind of a dynamic logic. It's one thing for a line of soldiers to advance forward, but if they spurt forward in a very intense stream and focused on one spot, that it's a temporal spatial dynamic where the
First of all.
temporal is just as important.
Hmm. So the a general principle here that I think might uh, resonate with our more general kind of thinking is to do with how resonant dynamics are require a container, but resonant dynamics also modify their container.
Yeah,
So that there's two time scales of variables or dynamical variables. There's a fast timescale variables which are to which well, fast and slow. And from the point of view of the fast variables, the slow ones are like boundary conditions
yeah,
which hold them in place in order to find standing waves, for example. But the slow variables are still variables. They do still change, and we call them structural variables. Structurals in tends to imply that it's something which is fixed, but it isn't really. It's something which is just slow changing.
yeah,
And that this might apply over multiple dynamical timescales, right?
yeah,
So
yeah,
to the internal milieu of a cell, the physical structure of the membrane might seem stationary, right? Given the speed
yeah,
of chemistry.
right.
But it's not stationary because there's a time scale in which we're very interested in the movement of the amoeba or the cell in its environmental context.
Yeah. Yeah,
Yeah.
so not only, when you move from the individual to the membrane, you have to, step up in your analysis. The primitives are different. the primitives of a membrane are the linear alignment. But then on
Yeah.
top of that, if you're examining in one time scale, you get a completely different set of laws than if you examine at a different time scale. So
Yeah.
that's yet another thing that
Yeah, it's an interesting example actually, because you can see, it's very tempting for a naive physics to assume that what's happening at the macro scale is some sort of coarse graining of what was happening at the micro scale. But you can see that a property like containment, that you have a membrane that doesn't have any holes in it,
yeah,
is like it just isn't captured by any coarse graining of the micro scale.
right, right, yeah, exactly right.
Good. Um, So I think that, this is something that which we don't often articulate, Charlie, but I'd like to have a go at saying why I think harmonic resonance is the answer to everything.
Okay.
Because, that's Steve's expertise, and that's the right time to do it in a conversation with Steve. Because uh, Steve knows that we've had conversations about harmonic resonance and, everything is a vibration, everything is a rotation, that harmonic resonance is how you communicate between scales and stuff like that. And I'm really excited about that and really on board with that. And I think that it's not just a way to do it. I think it's the only way to do it. I think it's the only way that makes sense. However, I haven't developed working models of how that works yet, or even published a paper about the vision or the ideas of that. So most of the scientific projects that we've proposed so far for the ABI have been based on variations of natural induction of learning in viscoelastic networks. So the model which I did of that based on particles connected by springs. The fast variables are the positions of the particles, and the slow variables are the lengths of the springs. So the lengths of the springs control the dynamics of the particles, but the distribution of particle positions over time modifies the lengths of the springs, and the feedback between those two gives you a learning process that's analogous to associative learning in a neural network. And because that's much better developed in my previous work, it makes sense to use that as a framework which we can investigate further in mechanical networks and chemical networks and other kinds of biological substrates. But I would like to take this opportunity to articulate why I think that's not the answer and why I think harmonic resonance is the answer, right? Um, so I think that a place to start is to think about this idea of multiple levels of organization and to contrast a harmonic resonance way of coupling levels of organization with um, other more conventional, more naive ways of coupling levels of organization. So, in physical systems in general, and complex systems more specifically, it's very common to treat them in a coarse-grained way, right? We know that there are subatomic particles, we know that there are atoms, we know that there's materials, we know that they compose together into larger and larger objects at different physical scales, all the way up to the cosmos. And sometimes we're interested in things the size of planets, and sometimes we're interested in things the size of subatomic particles. Sometimes I'm interested in the individual molecules within my mug on the table, and other times I'm just interested in the mug, right? And I don't need to worry about the molecules that it's made of. So one simple relationship between the micro scale and the macro scale is simply that there's a sort of one-to-one uh, um, locking together of movements in one with movements in the other. So that when I push my mug on the table, the translation of the mug is identical to the translation of all the molecules it contains, right? They just get moved along by the same amount. That means that what you describe with a coarse graining at the macro scale is a very ordinary kind of coarse graining, right? It's just a reduction in the detail that you're recording, but there isn't anything, hmm, how to put it? What I really want to say is that there isn't any topological folding between what's happening at one scale and what's happening at another. I don't know if that's well defined or not. Another way in which micro and macro can be related, but is also boring in a different way, is in a gas, all of the micro scale movements are disorganized in such a way that they effectively cancel each other out, and all you have left at the macro scale is just a pressure and temperature. Uh, so they're not locked together in the same way as they are in a solid, but there essentially isn't any interesting communication between one level and another. It's purely an aggregate. The macro scale variables are purely aggregates of the low scale variables. What's interesting in biological systems is that there are many levels of organization operating at different physical scales and at different temporal scales, but they're not locked together like they are in a solid, and they're not just aggregate relation like they are in a gas. There's something more sophisticated about the way in which the levels communicate. It needs to be the case, and it is the case in biological systems, that sometimes small differences at the micro scale have a big difference at the macro scale. And sometimes particular changes at the macro scale can cause specific reorganizations of the micro scale. Not in a one-to-one way that, this macro scale structure always means this micro scale structure, but not in a sort of just a blanket aggregate, any old set of molecules, so long as they're the right temperature, will do sort of way either, right? It's not one-to-one, but it isn't just a sort of boring aggregation. And I think the reason that harmonic resonance is so vital is because it gives us a way of understanding what that kind of underdetermined coupling could be. So it's not a determined coupling in that, this at the microscale always does that at the macro scale or vice versa, nor is it decoupled like the molecules of a gas and the pressure of a gas. But it's in between, it's underdetermined kind of coupling. And the principal thing, the principal key concept, the key principle that I keep returning to is the idea of harmonic locking between F and 2F, which sometimes I think about in injection locking, where you have something at frequency 4 and something at frequency 2, and they can lock together so that they can control each other's phase, but there are two different ways in which they can lock together and control each other's phase. And that means that when you know the phase of this one, or maybe I should put it that way around, when you know the phase of this one, you don't know whether the phase of the other one is that or that, right? And they're like 180 degrees apart. They're completely different, right?
Yeah.
But you do know it isn't anything else, right? It's one of those two things. So you have a 2-to-1 relationship there between what's going on at one level and what's determined at the other level and what isn't determined at the other level. And that kind of relationship means that if you only do local changes to your system, it will look like things are in lockstep, right? But actually, there is another alternative where things could be the complete opposite of what they were before and still be in lockstep. And that
Yeah,
kind of communication between levels is the interesting kind.
yeah, that in a Gestalt system, it would resonate at both and it create a rivalrous, unstable popping back and forth between the two.
Yeah.
Um, I think a very good example of all of these principles is the formation of the solar system. That you get this huge, immense a ball of gas that is so like faint and diffuse, it's virtually a perfect vacuum, but it's so massive that it actually has, size and shape. And the thing starts to collapse. And as it does, it um, it it starts to form orbits. And initially, the orbits are in all possible directions. So imagine the sun, and there's an orbit goes this way, and another orbit that goes that way, and every other orbit in between. But then at the macro level, what happens is that this is a giant swirl of very faint gas has an initial rotation to it. You know, it's a little curl of turbulence or something. And what happens is as these different competing orbital schemes fight it out among each other, you get a dominant rotation around the dominant plane, and then fainter rotations at every possible direction. And the faint ones have to, every individual orbit, every particle of that orbit has to pass back and forth through the dominant orbit. And when this happens over time, it eliminates all of the orbits that are out of alignment with the principal orbit. And that's how all of the orbits thin into a planetary disk. All right, so that's one level. And then the next level is that planetary disk, which is, you know, initially uniform. It starts to segment into lanes like you see in the rings of Saturn, and they have all to do with resonance that
Mm.
you know, planets at this level and at that level resonate, where this one goes twice around for this one every time it goes once around, and they interact with each other as they pass in their orbits, and that starts to create bands where you get a resonance, getting to Kepler's laws, that the mass concentrations happen according to a mathematical law, which is determined by a circular resonance of these things all going around. And eventually it narrows down to individual rings, which become individual planets. And so there's a perfect example of what you're talking about, that at the global level, you have this like a gas of particles. And at the local level, you have individual particles resonating with other particles. And between the two of them, they create first planetary rings and then actual planets.
Yes. It's important to recognize in that example that there are many possibilities for how the solar system could have turned out in its coalescence from that initial rotating disk, but not a smoothly, homogeneously populated space of possibilities. There are discrete possibilities where the resonance relationships are satisfied, and other discrete possibilities where the resonance relationships are satisfied. And in between, there are large gaps where it's disallowed. And
Yes.
that's important because it gives you a sort of linguistic space of possibilities where there are certain configurations which are allowed, which have a systematicity and compositionality to them. And there are certain configurations which are not allowed, which will not be stable, with which create big gaps in between them.
Yeah.
Mm. So I think that it's the only scheme I've heard of where you could have multiple levels of organization where the activity at one level of organization matters in a detailed way to the activity at other levels of organization without completely determining it.
Right. Yes.
So that you have flexibility in how things are, you would use the word reified, how things are um, coalesced or materialized at one level of organization. There's flexibility there. There's ambiguity there, which gets disambiguated in particular contexts.
Yeah.
Yep.
Um, but the space of possibilities obeys systematic laws from the level below, nonetheless.
Yeah.
Can I add a couple things?
Yeah.
Yeah.
So a couple. So I I agree with what Richard said about the sensitivity to big scale and tiny scale, that it's sensitive in both directions. So that attracts me to resonance as a solution. The other thing is that it unifies different domains, and you've really given some great examples of that, Steve. And I mean, we obviously the stuff we did in your basement with piezoelectric, devices is one of those examples, but also, you can imagine a giant speaker over a pan of water, and it makes an audio, sound, and then that becomes a frequency of waves in the water, which becomes, if there's sand on the bottom of the plate, that becomes a spatial distribution of sand on the beach, and so those three domains, get linked. And I think
Yeah.
to me, that's something that's deeply biological. If you hear a spooky sound at night, your heartbeat speeds up and your breath shortens, and so forth. So that attracts me to it. But the second thing that attracts me to it is, or third thing, is something where I have a ton of questions, and Richard is kind of in a different. We're still like trying to. There's really something we're trying to solve, that we're trying to get to. Um, and it's this relationship between phase locking, which is kind of the production of order, and then perception, which is the introduction of some type of disorder back into the system, where there's some sort of additional information that comes in and kind of moves everything around. And so, like, one of the questions I have is, and my suspicion has been all along, that organisms are required to sleep, like that there's two different types of resonance that happen in organisms. One is between them and the world, and another one is between them and themselves. And so they have to like shut the doors of perception, resonate with themselves to get back into phase, into congruency, like into coherence. And then they have to, after that's done, there's a specific moment where you can't sleep anymore, and boom, the doors of perception open again, and you're with the world, and you're somehow resonating with the world in a different way than you were just with yourself. And I wonder, so one of my questions for this conversation is, are you aware of other natural examples where systems go into phase locking and then spontaneously jump out of it, or vice versa, jump into it at some point? And like, what are there known triggers between those two states where like a solar system is forming and then it unforms for some reason, or vice versa, something is becoming disorganized and then it shifts phase and starts to phase lock. Um,
Question.
Mm.
Can't think of one
So
of.
we're interested in systems where coherence emerges spontaneously, but you're asking us about systems where the change in coherence is not monotonic.
yeah, like the way it switches back and forth, and for what reason and under what conditions. Um,
Yeah.
I mean, maybe
It
that's
um
maybe
it
that's
makes sense to me for the sort of biphasic, shall we say, nature of what you're describing. Makes sense to me for a couple of reasons. A couple of reasons in addition to what you've already said. So one is that if you have a system doing work on its environment, then by the very nature of doing work, it's going to incur wear. It's going to be perturbed or distorted by the work that it does. And resonance has a propensity to restore sort of perfection of form by sort of purifying things to exact ratios after they've been distorted, right? To clarify the message and move away from the garbage in between. But I think that it might not be possible to do those two things at the same time, to do work on the world and hold hold yourself robust to deformation. That instead it might be necessary to do work on the world uh, in one phase, during which you will also incur deformation. And then in another phase, you repair that deformation, but whilst you're doing that, you can't do work on the world. I guess I don't have a strong argument for why it has to be like that, why you can't, be half asleep and half awake at the same time, right? Doing work on the world and repairing yourself at the same time. But I do have a couple of sort of worked examples where which support it a bit, right? So in the
If you're a dolphin, you can sleep with one hemisphere at a time, though.
yeah, yeah. Um, so one is that it's very simplistic, really, but I sort of if you in order to be an agent, it needs to be the case that you are sensitive to the world, that the world needs to be able to do work on you. Otherwise, you can't form a memory of anything that happens or learn anything. But it also needs to be the case that those things you have learned or memories that you hold are robust enough that they can do work on the world. How can both those things be true? You don't want an organism and its environment to simply fall into equilibrium, where the organism is sort of, like plasticine pushed by the world, but also can't do work on the world because it's made of plasticine, right? It has to be able to be impervious, unaffected by the world whilst it's doing work on it. But it also needs to be sensitive to the world in order to be sensitive to the world, right? In order to hold memories or learn anything about it. Uh, so Friston does that, and many people do that by dividing the interface between the organism and environment into parts of the interface which are inputs, which are sensitive, and part of the interface which are outputs, which are not. But the way that I think about it with natural induction and some of the other systems that I've modeled is that instead of doing it with, this part of the interface is the input and this part of the interface is the output, I do it with all parts of the interface are inputs for a while, whilst I'm sensitive but inactive. And then all parts of the interface are insensitive for a while, whilst I'm active but insensitive. And you go back and forth between that pushing on the world and being pushed on by the world in a turn-taking way instead of in a constant rotation way that an input-output system would. And I think that you can get that going. Hmm. I don't know. Let's put it on our list of research questions of like how could you get how would one route toward agency differ in the necessary conditions from the other route towards agency, a sort of
Well,
a continuous input output model versus a pulsing um, input output model.
Uh, if you will forgive a crude analogy, but the process of ejaculation, that when you're target driven, very intensely focused, then all of a sudden, you blow. And then for a long time, it's like you don't care, you don't give a damn. And then after a while, it all builds up again, and off you go. It's a little bit like, the sun rises in the morning, and oh, it must be daytime, and that explodes you out of bed, and off you go and do your thing. And then at the proper time, the sun's going down, kind of dark, and then you retreat to bed. So
You
there's
could have used the refractory period of individual neurons for that, Steve.
oh yeah, there we go. Thank you.
Spiking neurons. Mm.
yeah. Yeah, and what's more mysterious about it is like when you set up a model, you can just toggle back and forth between the modes. But if it's going to be realistic, it's got to be there's something intrinsic to those modes that exhaust themselves,
Mm.
that somehow a they get to a point for some good reason intrinsic to the system itself that forces it to change to switch again. And it's not satisfied to be in harmony with itself and insensitive to the world, and it's not satisfied to be out of sync with it. it's not satisfied to lose itself in the world either, and just continue continue becoming a, a set of molecules among other molecules. It's I guess you could I think you could explain you might be able to explain. I hate to say this, but you might be able to explain that shift through natural selection. But
You didn't.
I know you're going to hate that. But the other shift, we have to come up with a good reason. Anyway,
You can think of like sleep as restorative, that you build up energy, and that very primitive animals don't sleep. And you go up a level, I think even like insects, like the housefly, does not often go to sleep. And you could say that the animals that do use sleep, they use it not so much to pass out and be inactive at night, but in daytime to give double the energy that they otherwise would have had, on the understanding that they can only do it for a limited time and then they got to go back to sleep. So maybe the evolutionary advance that brought us sleep was a way to double your energy output in one phase and then reduce your energy output in the counter phase.
Yeah. I mean, it's partly like hammering in a nail, right? I mean, you just can't do it by slowly pressing on the hammer, right?
Yeah.
hmm.
Once you give
However
one
long you
blow,
press for it, just the nail just won't go in, right?
yeah. And once you give it one blow, you can't continuously, you have to, recharge your arm and its position for the second blow.
Yeah. And in those refractory periods, you have a chance to adjust the next strike.
Yeah.
Right. But whilst you're striking, you really don't. It's like I'm already committed. The hammer is already on its way.
Yeah.
However it hits this nail is just how it's going to hit it, right?
Yeah.
There's no time for course corrections. But in
Yeah,
between strikes, you can say, "Oh shit, I bent the nail over. I should stop."
that's a really good example. Man, that's a great metaphor. Driving in a nail. Yeah, because you could exhaust yourself with this, use the same amount of energy to just push on the hammer and get really tired, and never get it done.
Yeah, I
Yeah.
mean the work would say that whilst you're pushing on the nail ineffectually, you haven't actually done any work, and so you haven't actually used any energy. It's like, yeah, but also the nail hasn't gone in. So, whatever.
Yeah, exactly. Exactly. Yeah, that's
I
that's
mean, so yeah, you make a good point, Charlie, about how resonance works across substrates, right? So it doesn't have to be bioelectricity doesn't have to be the answer to everything, and physical acoustic vibrations don't have to be the answer to everything, and chemical oscillators don't have to be the answer to everything, but all of those things can be communicating in the language of frequency and resonance smoothly between one substrate and another, so long as they have some effect at the right frequency. And the other thing that's beautiful about it is that um, it has this sort of specific action at a distance, like transmitter receiver kind of behavior that's very general uh, and enables you to do things which are like a network, a sort of point-to-point communication without having wired connections and um, like you would in a configurational network. And lastly, the difference between I don't know if it's lastly, but the difference between the perceptual aspects of resonance that you recognize something or perceive something because it resonates with your the frequencies of your expectations, but also that it's in reverse that the waves can um, coordinate to produce interference patterns at another level of organization, which actually move stuff, which apply physical forces to things, right? Um, so that it isn't just a matter of a sort of, how can we put it, like a mathematical relationship between um, sensed variables and internal representations, but a causal relationship in both directions.
A
Um,
good example is visual perception, especially in the monocular case. If you see like a perspective a drawing, then what happens in your mind is this two-dimensional stimulus gets expanded in depth, as if you did an extrusion of the image from near to far, creating geometrical planes of probability of the location of each of those edges. And what happens is that in the extrude, like for instance, you have a cube viewed at an angle, creates a certain pattern, and you extrude that pattern in depth. And then you say, in this extruded pattern, what are the possible interpretations? And if the cube is ambiguous, then there'll be this one and there'll be that one. But each one is self-consistent with itself and rivalrous with the other. And
Yeah,
it's an example of, exactly that kind of thing, that the ambiguity of the visual stimulus in depth creates a projection that fills in that stimulus at all depths. And then internal feedback within that figures out which ones make a coherent, stable whole.
good. So, Charlie, for I could spend 5 minutes telling Steve about what I've done recently with
difference tones.
doing, yeah, difference tones and Boolean functions and such like. Would that be useful? Is there something else that we need to do with the
Yes,
remaining 10 minutes?
yes.
Go for it. Yeah, no, that was top of mind for me too.
Okay,
Under
cool.
what conditions does, yeah, does it?
So, so far, an undergraduate student of mine, Percy Baker, and I have been working on just doing some very simple uh, wave-based Boolean functions. Um, we assume that a variable is represented by a particular frequency, and the value of the variable is represented by its phase. So if you want to read the value of a variable over time, you need to know what phase to read it at, because if you read it at pi half a wavelength out of phase, you'd get the opposite value that you were reading for that variable. You can think of the value of a variable at an instant as well, if you like, that it's oscillating up and down, and at a particular instant it has a particular value. But if you want that value to be meaningful over time, then you need to know a phase so that you're reading it at a particular phase so that it holds that value constantly over time because you weren't looking at the times in between, right? So then a two input function is going to be two waves of different frequencies. And what we want to be able to do is uh, read off different Boolean functions of those input waves. So we can think of the input as a combined wave, one wave added to another. And we might want to do something such as uh, assess whether or not the waves were in phase or out of phase, which we can interpret as whether they satisfy XOR or not, right? So if the inputs are different, XOR should be true, and if the inputs are the same, then XOR should be false. Uh, so that function is, like everything else in this way of thinking about variables, not going to be a constant. it's going to be a wave as well. So we're going to have a wave which represents the XORness of our combined input, and whether the XORness is high or the XORness is low is going to depend on the phase with which we read it, right? If we read it at one particular time, it'll say that yes, they're the same. If we read it at another time, it'll say no, they're different from each other. Now, that the wave that you need to do that is, in a sense, not something that you need to calculate about the input. It's almost something that you just need to look at the input in the right way to see that it was already there. Specifically, um, the XOR wave is simply the difference tone. It's the interference bands or the beat that you would get between the two frequencies. So if you have one input frequency, which is, I don't know, f of 15, and another which is f of 16, then the beat is of frequency 1, and you can see that beat increasing on that frequency. And when it's low, that means that the two waves are canceling out. And when it's high, that means the two waves are um, positively interfering, constructively interfering. And that's so that phase, that point in the phase of the beat wave, the difference tone, is saying, well, this is when they are um, equal. And the low amplitude is saying, well, this is when they are unequal. This is when XOR is true, right? So depending on when you read that uh, difference tone, you get to see, well, when are they the same and when are they equal, right? That's what you're reading when you do that. This way of thinking about it says that I'm not really converting the input or calculating something from the input. I'm just looking at the input in a particular way, right? The difference tone is already there. I just need a way of drawing out um, um, a perspective on the input to see the difference tone and the phase of the difference tone that's there. Um, the next, is that okay so far?
I think so.
Hmm.
I'm not sure where you're going with this.
Hmm. Me neither. Uh, so the next thing is that if you represent the input by just the phase of the difference tone, you have lost information because the difference tone is only one frequency and one phase variable, whereas you started with two. You can't reconstruct the wave exactly just from the difference tone. But there is another tone which gives you exactly the information that was lost by measuring the difference tone, and that's the average tone. So whereas the difference tone is F1 minus F2 over 2, the average tone is F1 plus F2 over 2. And it's neither F1 nor F2. It's not the same as either of the inputs that you started with, but it's the average frequency. And if you multiply that fast tone by the difference tone, you reconstruct the combined input that you started with and you haven't lost any information. So I was quite pleased with that, that now I have a way of looking at the input, which says I'm going to split the input into the difference tone and the average tone. And the difference tone tells me what the XOR of the input is. And but I haven't lost any information because I was also keeping the average tone. And in that way, I can think of the transformation that has been done between F1 plus F2 into S times D, right? The difference tone times the sum tone. That transformation, since it didn't lose any information, I can also think of that as a rotation. Right? I'm rotating through a way of looking at it where I looked at it as a two-dimensional thing represented in F1 and F2, and I transformed it into a different two-dimensional basis, S and D, which didn't lose any information. And I can carry on doing that rotation and get back to F1 and F2 to get back to the original basis. So that means that computation or calculation can be lossless. It doesn't lose any information. It's just a sort of choosing to look at a particular part of the information and choosing not to look at another part of the information, right? But you need to change the basis to do that, right? Because if you start with F1 and F2 and you say, well, I could look at F1 and I could ignore F2, and I could look at F2 and I could ignore F1, but I haven't really done any transformation of anything, right? I've just looked at part of what I started with. Whereas when I transform them into the difference tone and the sum tone, now I can see the XORness of the input. I can see whether they are the same or different. But I also have to keep the average tone, which is like a sort of clock, uh, in order that I didn't lose any information. I've got one more step that Percy has done for me this week, which is that if you if you can use the difference tone to calculate the XOR of the inputs, that is the same as uh, Hebb's rule. Because Hebb's rule is what? Hebb's rule is the weight between two variables represents whether those variables are positively or negatively correlated, right? So the phase of the difference tone tells you when they are positively correlated and when they are negatively correlated. So if I give you two inputs with a beat and you find the phase of the difference tone that fits that, that's like learning not are they correlated or are they anti-correlated? It's like learning when they are correlated and when they are anti-correlated because they're going to go back and forth between those things. But that's the sort of wave-based version of Hebbian learning, right? Instead of learning, are they positively correlated? Are they negatively correlated? You're learning, well, their correlation is going to change, but I need to know how quickly it changes and what the phase of that change is, right? And now after you've learned the phase of the difference tone, which is like learning the weight of Hebb's rule, now you can use that to generate two inputs that satisfy that correlation. Give me a phase of F1 and a phase of F2, which matches that difference tone envelope. And there are multiple ways of putting those two phases together that will match the phase of that envelope so that it's a generative model of the input. In other words, you show me some inputs which are correlated now and anti-correlated then. And if I know that they're correlated now and anti-correlated now, I can generate some inputs which satisfy that. And there are multiple ways of generating inputs which satisfy that. So you can go back and forth between a distribution of inputs where you learn a weight, and having learned a weight, you then generate a distribution of inputs. And so that's the two-way relationship that we need. And that two-way relationship is just what we were talking about at the beginning, about there being fast variables and slow variables. When the slow variables are treated as though they are static boundary conditions, they constrain what the fast variables can do. But when the low-dimensional slow variables are treated as variables, they become learning variables, right? That the fast ones are pushing them around so that they hold a memory of what the fast ones were doing, and then they push back again, which is a recall of that memory. So it's very minimal, very basic, almost nothing at all, but it does have, I think, some of the elements of the fundamentals that we're looking for.
That's we might have to cut it off right there.
Mm.
We've got to start another meeting at 10, so but Steve, that was wonderful. Thank you. I hope that stimulated some th is that your crow?
It's my crow.
Nice.
They're demanding service.
Awesome. Oh,
Nice
that's
to see
so
you,
great.
Steve.
Yeah, it's wonderful to see you. I hope we can do this again in a couple of weeks. Um, and maybe have,
I
have
think he's gone to feed the crow.
some tighter yeah. That was great. Okay, I'm gonna stop
Yeah,
for
we better skip over to Josh, hey?
yeah.
Bye for now, Steve, if you can still hear us.
Yep. Bye bye.